This work presents a framework to allow bipedal robots to work on constrained footholds that control the discrete transition of angular momentum. The goal is to have underactuated robots traverse different terrains with predefined footholds. The major difficulty is the underactuation and the precise foot placement, which leads to non-periodic behaviors. To tackle it, we separate the robot dynamics into output dynamics and underactuated dynamics. With sufficient control capability of the robot's actuators, reasonable output can be tracked by a low-level controller. The idea is then to focus on the resulting underactuated dynamics and stabilize it using controllable outputs. A question naturally arises is what is the desired behavior for the underactuated dynamics? The equation of motion shows that the continuous dynamics is nonlinear and has no closed-form solution, but we do have an explicit impact map. We then use the linear inverted pendulum model to approximate the continuous part of the underactuated dynamics. Based on this approximation, we can characterize the desired behavior for the underactuated dynamics. We know that the criterion for limb model being able to take a step can be fully described by post-impact states lying in this blue triangular region on the face portrait. This can be characterized by three variable conditions, where E stands for orbital energy. Similar conditions transfer to robot dynamics with a tightened bound on orbital energy. Now the stabilization of the underactuated dynamics is defined as post-impact states lying in this variable region represented by blue strip. These conditions can be achieved using closed-form impact map, where these quantities are determined by stone configurations. These are the underactuated states, and this left us with only the COM vertical velocity to regulate the post-impact angular momentum. To remain viable, the COM x position is regulated by step duration, which is computed from lip time to impact function for estimated pre-impact COM x reaching some ratio epsilon of the current step length. The last two conditions can be achieved by controlling the vertical COM so that the post-impact angular momentum corresponds to the desired orbital energy E star. And together with other polynomial-based trajectories, all the outputs are then tracked using a task-space QP controller. This method is demonstrated in simulation with Amber and Cassie model. Here are some results with periodic stones on Amber in MATLAB. Starting with same initial condition, all of them converge to periodic walking. Then is the random stepping stones and the resulting face portrait. We can see the evolution of the face curve in continuous time is very similar to the underactuated lip model. As shown in the video, the user-determined parameter epsilon affects how lean forward the robot is at pre-impact, and the E star is positively related to the robot's COM forward speed. Here are the results for stairs and flat ground stepping stones on 3D Cassie in gazebo simulation. Working on randomly generated stepping stones is also demonstrated. Our method is applied on the sagittal plane and the H-lip stepping is used to stabilize the coronal plane. In all scenarios, with foot placement closely tracked to less than 0.5 cm error, the proposed method stabilizes the orbital energy close to desired, which is the black curve, and the actual COM vertical distance to the slope is also stabilized to near desired. This concludes my presentation. Thank you all for your attention.